Let's learn what the energy density is. Density is a familiar concept. It is the amount of quantity possessed by 1 cubic meter of a substance. Energy density is the number of joules that can be released from 1 cubic meter of a fuel. So let's define it as the ratio of energy divided by volume. Here in SI units, we expect the unit of joule per cubic meter. This energy is actually the potential energy, nuclear or chemical, depending on the type of reaction it's defined. In this table, you can see a few examples. Wood, coal, gasoline, they are chemical fuels. So the type of reaction is chemical here. The value here is measured in the unit of megajoule per cubic meter. For the wood, 10 to 4. For coal, between 20 to 60, 10 to 6, and so forth. Uranium will undergo the nuclear fission. It's not a chemical fuel. But anyway, the amount of energy is too much. You see 1.5, 10 to 15. Actually, the nuclear reaction, will produce a tremendous energy. Deuterium, tritium, they are also nuclear fuels, but they undergo nuclear fusion. Anyway, 6 times to 10 to 15. It's very huge energy. Let's answer this question. A fossil fuel power station burns coal. It has an efficiency of 25%. What does it mean? 25% means that in Sankey diagram, if we have the total input energy of in, 25% is going to be the useful and 75% is the degraded, dissipated energy. Okay, and generates 1200 megawatts of useful electrical power. Guys, this is not the value here. This is going to be the energy. So here we should put useful energy, not useful power. So let's convert it. The energy density of the coal is given. 1 cubic meter will produce 42 gigajoules of energy. Calculate the volume of the coal burned. So we are looking for the volume of the coal. But here I see something. Burned every minute in this power station. Every minute is very important concept. Means that the amount of energy here is going to be based on 1 minute. You know that power is energy divided by time. So here we can say energy is power times T. Okay, so anyway, for 1 second, the energy produced is 1200 megajoules. Because megawatt means megajoule per second. So each second, this amount of energy. In 1 minute, as it's 60 seconds, the amount of energy is 60 times larger than this. Based on that, the total useful energy out is the amount of energy produced in 1 second times 60 seconds. It's the total useful output energy in 1 minute. Okay, here I see it's just 25% of the total energy input to be 1200 10 to 6 times 60. How can I find the E? It's very easy. I can divide the right side by 0.25. So to find energy, I can just divide the useful output energy in 1 minute by 0.25. So the amount of energy is this, 288 gigajoule. And here I have already saved a 10 to 9 in form of a giga. Okay? Now let's find the volume. It's very easy. I know that according to the given value, in 1 cubic meter, this fuel will generate 42 gigajoules. Now I'm gonna have 288 gigajoules. How much is the volume of the needed fuel? It's very easy, just I have a proportionality here. Volume is gonna be 288 times 1 divided by 42. That's all. The answer is 6.9 cubic meter. This is the total volume of the fuel needed in 1 minute in this power station according to the given energy density. When a camping stove that burns gasoline petrol is used, 70% of the energy from the fuel reaches the cooking pot. So the efficiency of process is 70%. The energy density of the gasoline is 35 gigajoule per cubic meter. Calculate the volume of the gasoline needed to raise the temperature of 1 kilogram of water from 10 to 100 degrees Celsius. Assume that heat capacity of the pot is negligible and specific heat capacity of the water is 4.2 kilojoule per kilogram Kelvin. It's actually 4,200 joules per kilogram Kelvin. Let's save the values here. First of all, let's find how much energy do I need for that real amount of energy. The water will participate in a heat transfer process and will have a temperature raised from 10 to 100. So it's gonna be 90 degrees. 100 minus 10. C was given, mass is 1 kilogram. Let's plug in the values. And finally, it's gonna be 0.38 megajoule. Actually, here I have already saved a 10 to 6 for mega to make it concise. Okay, now keep in mind that the process has just 70% efficiency. Means that although the fuel will release 35 gigajoule when you burn 1 cubic meter, but the problem is just 70% of that is useful. So actually the useful energy density seems to be just 70% of 35. So let's put it here. For 1 cubic meter of the burned fuel, we have just 70% of 35 10 to 9 joule as the real useful energy. So here I need this amount of energy. I will export it from here to here. And then this is my goal, the volume of the fuel I need for this process. So it's very easy, just you can solve this proportionality. Volume is gonna be, let me write it for you. Volume is gonna be 1 times 0.38 10 to 6 divided by 0.735 10 to 9. And the answer is gonna be 0.16 10 to negative 3. And if you remove this 10 to negative 3 cubic meter, you can substitute that for 1 liter. So it's gonna be 0.16 liters or 160 cubic centimeter. This is the volume of the fuel needed for this process. Thank you for watching this video. We are done. Take care. See you.